Okay, so let's just start this session again. So in that session, we talk about spatial functions. When we say spatial functions, we say that we are often encountered by spatial functions in many engineering problems because they just appear and they don't have corresponds. So in that case, we would like to sort of using this spatial function to express it. One way to think of it is it's actually just a notation. You can write this whole thing in an engineering problem, or you use a simple notation as a replacement. So for example, in this equation, you can put this whole integration into it, and this equation will look very large. Okay, so that's one of the thing you can do, but uh, as a simplification, we sometimes like to use a simple form to do it. A simple form as a simple notation, just put it here, and then we know what it is, and that makes the equation more concise and easier to read. Okay, and then the next thing is the basal function has to be defined this way. And then, of course, it has the series representation by this. Uh, recall that whenever we have any functions, uh, as long as they fit certain properties, you can actually use summation of series. It's sort of like an expansion, series expansion to represent the function. So let's see, this is a function of u, and it could be represented by this series. This series. All right. So if if to understand this, let's take a look at the uh, Taylor series expansion. Taylor series expansion. I think you have learned this in some fundamental mathematics. So let's see, Taylor series. You see, it's a representation of a function as an infinite sum of terms that are calculated from the values of the function's derivative at a single point. Okay, so uh, for example, a function a function can be represented at a certain point a by this function, and if it goes to infinity, then it will be more and more accurate, and eventually that representation is equivalent to that f of x of x f of x. Okay, and then also there are other series type of representation. In other words, you can sort of see this as a vector. A vector, for example, two-dimensional vector can be represented by 0 1 and 1 0, right? Any two-dimensional vector can be represented by 0 1 and 1 0 because they are orthogonal and unit vector. Okay, so that's like the concept, except it is in the functional domain. This is like the basis. If we see it this way, this is like a basis in the vector. In the vector domain, we have basis vector, right? 0 1 and 1 0, that is the basis. Now those things are like basis. So basis will composed of the original function f of x. Okay, and then let's take a look at the spatial function. If you just Google spatial functions, and then you will see a list of a lot of spatial functions. So for example, I find a PDF function, no, a PDF file. You can try to search and take a look at it. Let's zoom in a little bit. You see there is a gamma function, right? Gamma function. And then gamma function, of course, gamma function can be, as we mentioned in Taylor series, it could be expanded and represented by some series, for example, Taylor series. So there are infinite products. And then, of course, then you have Jacobian functions, uh, hypergeometric functions, so on and so forth. So just to summarize, we have a lot of spatial functions, and the basal function, gamma function, and beta function, those are the types that we encounter more often. Okay, so let's come back to this slide. Okay, and so it has a series representation by this, and some of the examples of the PDF are given in the figure, which we'll look later. Okay. Um, so using the series expansion of this expansion, that is the expansion of this, and you put this whole thing into here. You put this whole thing into here and make a simplification. You see P of X is expressed in this way. You have a term multiplied by a summation of this thing. It's expressed in infinite series form. So sort of like this as a replacement for the I. Okay, and then let's come back to this PDF textbook again. Just to recall, we are at page 26. And note that for lambda equal to 0, the non-central chi-square PDF reduces to the chi-square PDF. The non-central chi-square PDF with V degree of freedom non-centrality parameter is denoted by this. So it's a chi with the prime, and then V to the square, and then parenthesis lambda. That is a notation for non-central chi-square distribution. Okay. And we have mentioned about 2.6. Now we take a look at 2.6. This 2.6 has V equal to 2, and then lambda 4 equal to something like this. Lambda to the 8 is something like this. Lambda to the 12 is something like this. So on and so forth. It just keep moves on. And then, of course, it's understandable if you have more and more random variables. It's more spreading out. It's more spreading out because of the larger variance. Right? Okay. And then let's go to the next page. The mean and variance, which is always the concern of our interest for random variables. So for example, this expectation of x equal to degree of freedom plus non-centrality parameter. Variance of x equal to 2v plus 4 lambda. Then we will denote the right tail probability as this, which is the Q chi-square non-central chi-square lambda of x equal to x to infinity p of t dt. And then it can be numerically determined by a MATLAB program Q chi square m. Right, and I believe if you try to use Python and C and other programming languages, you still get those kinds of packages because it's very common. And then let's go to the F distribution. FPDF arises as a ratio of two independent chi-square random variables. Specifically, if x is equal to x1 divided by its degree of freedom 1, and then the whole thing divided by x2 divided by its mu2, its v2, I'm sorry, v2, which means that which means you have a x, then you have a x1 and you have a x2, and that x1 is chi-square distributed, x2 is chi-square distributed, and x1 x2 are independent, and x has the FPDF. Then you can imagine chi-square distribution has been very complicated in its formula. Now we are making a ratio of a complicated random variable. It's getting more and more complicated, as you can imagine. So it's given by this p of x equal to this thing, and of course then it's defined for all region of the real numbers. However, for x smaller than 0, it has zero probability. Okay, and then let's just take a look at the formula in some details. You have a random variable divided, which is divided. No, it's composed of a ratio of two random variables, meaning that x1 divided by x2, and then its form is, of course, is already parameterized by v1 and v2. Right? It's already parameterized by v1 and v2. Now we have v1 defined because it has been defined here. So we're looking at v1 that is defined. Then we have v2 that is also defined here. And then it has exponent v1 over 2. v1 over 2. Okay. And then the next thing is we take the ratio of this random variable by a b function, which we will explain later. And then the other part is the x to the v1 divided by 2 minus 1 over this 1 plus v1 divided by v2x, parenthesis v1 plus v2 over 2. This whole thing is well defined, so we don't have problems with this, right? v1 x, everything is defined. Okay, then the only thing remains is the b function. So we'll take a look at the b function. B function is the beta function. As previously we mentioned about spatial function, this is one of the commonly encountered spatial function, b of u and v, that is called the beta function. and which can be related to the gamma function as follows. B has two parameters. Maybe I should say more accurately, it will be argument, parentheses of two arguments. One is u, one is v, then it's gamma u multiplied by gamma v divided by gamma u plus v. And of course, we have defined the gamma function before, so there should be no issue with no confusion with the beta function, because it's been defined by gamma function, and gamma been defined before. Okay, so we will denote the PDF as FV1, V2, because they have parameterized by the two parameters as an FPDF with V1 numerator degrees of freedom and V2 denominator degrees of freedom. So this sort of a name, numerator, meaning that it's in the numerator here. 分子 numerator 是分子的意思 and denominator 分母 in the denominator. Okay. But it's just a name, you know. V2 is in the numerator here, so it's not a big deal. Okay. Some examples of the PDF are given in figure 2.7. Okay, we will take a look later. The right tail probability then is denoted by Q F V1 V2X and must be evaluated numerically. As we mentioned, it has no closed form. If something has closed form, we are always happy with that. But if it has no closed form, then we will just say we evaluate it numerically. And there is a course that is called numerical methods. 数值方法，有一门课叫数值方法。所以如果你们去修那一门课，你们会学到很多怎么做积分，怎么算一些很难算的积分的一些计算方式。Okay, so that class is going to lecture about how to numerically evaluate some complicated integral form or even derivative. It can be evaluated with some numerical approaches. If you recall, some years ago when you were learning a Newton method, 牛顿法, or something like that, they are all in the category of a numerical method. And the mean and variance are like this: E of x is equal to v2 over v2 minus 2. Variance of x is equal to 2v2 to the 2. Remember, notice that there is this is like exponent 2 here, and then parentheses v1 plus v2 minus 2 for v2 in different regions. Okay, for v2 in different regions. So this is a expectation variance. Then there are some properties. As v2 approaches infinity, x will approach x1 over v1, and distributed by chi v1 to the 2 over v1, since this thing will approach 1. Okay, right. So let's take a look at this figure 2.7. 2.7. Then you see it's more and more like a Gaussian distribution. It has sort of has a some kind of center here. It's more like probability being concentrated on this region and then spread out at the right hand side. And then at the left hand side it goes to zero. It goes to zero as x goes to zero. And for V2 like 100, for V2 like 50, for V2 like 10, it has different shapes. And this is all for V1 equal to 10. Okay, so this is a probability density function. And then there, up, up to this point, you may be wondering about one thing. That is, how come we are talking about V2 larger than 2 and V2 larger than 4 if V2 is smaller, is not larger than 2, then what's going to happen? If V1, if V2 is not larger than 4, and what happens here? The answer is it does not exist. It does not exist. This may seem strange, but in some random variables, the expectation and variance do not exist in some situations, and this is one of the case. So we have to clarify that when it is larger than 4, then it's like this. But let's say v2 is equal to 3, then what's going to happen to the variance? The answer is it does not exist. All right. So that's the F distribution. And then let's continue on to non-central FPDF. This central PDF is ratio of chi-square. And now non-central is the ratio of non-central chi-square. Non-central chi-square. Okay, so we have two random variables that is non-central chi-square. Of course, they have to be divided by their degree of freedom. V1 versus x1, and then V2 versus x2. And then you take the ratio. You take the ratio, then you will see chi-square. I'm sorry. You will see this x distributed as FPDF and non-central version is a non-central. And then this is additional explanation for x1 distributed by chi-square non-central. There is a prime here. See the prime means non-central, and it has non-centrality parameter lambda, and then x2 distributed by x by lambda, by this no, by this chi-square v2, and they have to be independent. uh I have to make a correction here. X2 is central chi-square, as you see here, is central. The non-centrality exists for x1, and x2 is central. No, I would say it would be the ordinary chi-square. And then x1 and x2 are independent, and x has the non-central FPDF. And it's denoted by this F prime, because non-central thing we denote it by F prime. Then it will be just a notation. It has no particular meaning. It's not like you take a derivative of something. It's not. Alright, okay. And in different textbooks, you may see different notations, but the important thing is you know what it means. Okay, the, the meaning of the notation. That's what it means. That's what it matters. Okay. So here it's not like when you take the differential equations, when there is a prime, it means derivative, but this is not. This is not. Okay. And it has a as a function of lambda as a non-central FPDF with V1 numerator and V2 denominator degrees of freedom and non-centrality parameter lambda. Its PDF in infinite series form is like this. Okay, let's take a look. It doesn't look very simple. It doesn't look very simple. Uh, let's see. We have a P of x exponent to the lambda. Of course, the lambda is defined. Okay, and then we have a k as a dummy variable. It's actually the index of the summation. And then Basel function. Again, the Basel function at this point. And then the Basel function, the v parentheses 1 over 2 v1 plus k multiplied by x. X is the argument of the function. v1 is the defined degree of freedom. v2 is the degree of freedom, and then k is the index. So everything is defined. It's a little bit complicated. Okay. And then let's go back and look for lambda equal to 0. You would expect what what are you expecting to see to for lambda equal to 0? It would be central version of the F distribution, right? You would expect when lambda is 0, then it would degenerate back to the central version. Okay, that's what we are expecting. So if we do the mathematics, and then of course in the practice problems there would be such practices, um, it will reduce this to the central version, which we call ordinary version. Sometimes its mean and variance are mean like this, mean like this. Okay, it has v2 and lambda, and then v1, v2 minus 2, right? And then variance of x, variance of x, and that variance of x equal to 2 v2 over v1 to the 2, and then everything is defined v2 v2 v1 v1 and then lambda. It's a bit complicated but reasonable, right? Reasonable, understandable. And then v2 larger than 4, it will be something like this. And then the right tail probability is denoted by this. When we're talking about right tail, it means that we're talking about, for example, distribution like this. We're talking about probability in this region. That's the right tail, right? That's the right tail part. So that's something like that. And then when v2 is large, it approaches infinity, then f prime reduces to chi-square v1 prime 2. Okay. And then the next chapter we are going to talk about Rayleigh and then Ricin. Those are also common examples we will encounter in engineering problems. But for this session, let's take a break for now. Okay, and then yeah, take a break.